Okay, good afternoon. I think I'll start now. Ritoban, can you please confirm if you can hear me?
Yes, sir.
Okay, thank you very much. And so I am taking the class from Nalanda Classroom, and I have started the recording. I have also shared my screen. So what we'll do is that we'll continue our discussion on these concurrency control protocols. So just a quick recap that we talked about this requirement of ensuring the property of isolation in transaction processing. And as we have seen that it means that when we have a number of transactions getting executed simultaneously or concurrently, then we have already motivated why we cannot allow all sorts of possible interleaving of the instructions of these transactions. While we definitely would like to ensure concurrency, we still would not like any arbitrary form of interleaving of those instructions from various transactions. And hence, we said that the schedules, that is the collection of transactions and the relative ordering of their instructions, execution of those instructions, so which we called as a schedule. So the schedules should be restricted to certain so-called quote-unquote good schedules, and which we said good schedules are, for example, serializable schedules, which could be either conflict serializable schedules or view serializable schedules. We talked about those. And in this particular chapter, we have started looking at different protocols for ensuring that the generated schedules under those protocols, they are indeed serializable. And we have seen that the first approach that makes use of locks, which we call the two-phase locking protocol. So in this two-phase locking protocol, if we restrict in the concurrency control manager, then the generated schedules are going to be conflict serializable. And we have talked about the growing phase and the shrinking phase and why it is called two-phase locking, and the fact that there is a lock point when a transaction has acquired all the necessary locks, and after that it is going to only release those locks, so which is called the lock point. And the equivalent serial schedule is the one which are ordered in terms of the lock points of those transactions. And we have also taken a couple of variations which are strict 2PL and rigorous 2PL locking, and we have seen that they provide added advantages of being cascadeless schedules being only generated. We also have discussed that although two-phase locking indeed generates conflict serializable schedules, the schedules generated under two-phase locking are not necessarily deadlock free, and which is, as we said, is a necessary evil which we have to live with, even though we are able to achieve uh, good concurrency um, features like conflict serializability in the generated schedules under two-phase locking. So that is what we have studied so far. Now what we'll do is that we'll talk about another kind of protocol, and which do not make use of locks, and these are called timestamp based protocols. So we'll take a look at some of those here. So what happens is that, so just remember that in timestamp based protocol, in the vanilla version that we are going to discuss, so they do not consider any form of locking at all. Okay, so but it's a completely a different kind of approach. So what happens is that in timestamp based protocols, each transaction is issued a timestamp when it enters the system. So a transaction starts its execution and it gets a timestamp. Now, so each transaction Ti will have a timestamp Ts of Ti. Okay. So now if there is an old transaction Ti, that means Ti entered, say, at 10:30 a.m. and it gets a timestamp of 10:30 a.m. and the transaction Tj enters at 10:31 a.m. So it gets a timestamp of 10:31 a.m. That's all it is. So the later transactions get a higher value of the timestamp. Now the protocol manages concurrent execution such that the timestamps determine the serializability order. So when we talk about such serializable schedules, we also need to think about ordering of the transactions in that equivalent serial schedule, and that is what is called the serializability order. And as I just now refreshed our memory of what we had covered in our last week's class, that for 2PL the serializability order is determined by the positions of the lock points. Now here for this particular timestamp based protocols that we are going to discuss, so for them the serializability order is basically the order of the timestamps of the transaction. So if a transaction Ti enters the system at 10:30 and Tj enters at 10:31 and Tk is at 10:32. So if the schedule that gets formed out of these Ti, Tj and Tk using timestamp based protocols, so that will ensure serializability, where actually the order of execution of the transactions in that equivalent serial schedule would be the order of these timestamps Ti, Tj, Tk. That means 10:30, 10:31, 10:32. If these are the timestamps, then the equivalent serial schedule will be Ti, Tj, and Tk. So of course I mentioned Ti, Tj, and Tk in that order, like IJK order is same as 10:30, 10:31, 10:32. But of course we could have said Ti at 10:30, Tk at 10:31, and Tj at 10:32. So in that case, the equivalent serial schedule will be in the order of that Ti, Tk, Tj. So it's that simple. Okay. Now, what is that protocol? So the protocol actually maintains for each data queue two timestamp values. So one is the write timestamp, or W timestamp, is the largest timestamp of any transaction that executed a write queue successfully. So again, we are only talking about read queue and write queue. So if there was a transaction that, so just to clarify, so this timestamp is for the transactions, and also for every data item we have a write timestamp and a read timestamp. So write timestamp of queue is what? It is the largest timestamp of any transaction that executed a write queue successfully. So assume that the transaction Ti at 10:30 and the transaction Tj at Tk at say 10:32, they both successfully executed write queue. Then because 10:32 is higher than or larger than 10:31, so write timestamp of Q after Ti wrote to it will become 10:30, and after Tk successfully wrote to it, the write timestamp of Q will be 10:32. Now, read timestamp Q is the largest timestamp of any transaction that executed read Q successfully. So if Tj reads this particular data item successfully, which is the largest one, if that is the case in this example, then this read queue will become 10:31. Now, what is the protocol? So this timestamp ordering protocol ensures that any conflicting read and write operations are executed in timestamp order. So suppose the transaction Ti issues a read queue. Now, if the timestamp Ti, that is the timestamp of the transaction that has issued that read queue instruction, that is less than or equal to the write timestamp of Q, then what is happening? The Ti needs to read a value of Q that has already been overwritten. Why? Because you see that in the equivalent serial schedule, this Ti would come before the transaction that wrote and updated the W timestamp of Q. So what is happening is Ti is now trying to read, but already the write timestamp of Q is greater than this timestamp of Ti, or equal to. That means that this is trying to read this Ti is trying to read a value of Q which has already been overwritten by some transaction that set that write timestamp value of Q. So for example, when say the transaction say Ti is trying to read say Q, and Ti has a timestamp of say 10:30, but already we find that the write timestamp of Q is say 1035, maybe some transaction T10 already wrote it. So that means that T10 mind it is always going to come later in the equivalent serial schedule. So it cannot so happen that I am allowing this transaction Ti at 10 with a timestamp of 1030 reading a value of Q, which has already been written by the T10 transaction with the timestamp of 1035, having set the write timestamp of Q to 1035. So this read operation is rejected and Ti is rolled back. And if it is greater than write timestamp of Q, then the or equal to. So equal to means that it is. So we can consider one of them as strictly less than. The first one we can consider strictly less than Q, write timestamp of Q. So if timestamp of Ti is greater than or equal to write timestamp of Q, then the read operation is executed, and the read timestamp of Q is set to the maximum of whatever is the current read timestamp of Q and whatever is the timestamp of Ti. So it is very simple that when this Ti is trying to write, is trying to read Q, then we check the write timestamp of Q, and then if the first condition is satisfied, then this Ti is not allowed to read, the read operation is rejected, Ti is rolled back. Otherwise, that Ti is read operation is executed, and the read timestamp of Q is set to the max of read timestamp of Q and TSTI. Now for write, so if Ti issues a write Q, then if TSTI is less than write timestamp of Q, then the value of Q that Ti is producing was needed previously. So some other transaction with a higher timestamp has already read and proceeded the value of Q. So it read the value of Q and already proceeded. And now this Ti being slow is coming and trying to write it. So the value which it is going to write, that was supposed to be read by a transaction which was coming later, but that already went ahead and read the value of Q and had successfully read the value of Q and had also updated the read timestamp of Q, and hence this transaction Ti, when it is trying to write the value of Q, so that already is stale. So the write operation is rejected, Ti is rolled back. Similarly, if the timestamp Ti is less than write timestamp of Q, then Ti is attempting to write an obsolete value of Q. So another transaction has already written the value of Q, and now later on, Ti is trying to write, although the timestamp of Ti is less than the timestamp of the transaction that wrote successfully that value of Q and had updated the write timestamp of Q. Hence, this write operation is also rejected and Ti is rolled back. Otherwise, the write operation is executed and the write timestamp of Q is set to the timestamp of Ti. So that is simply the protocol. That's all. And so if we consider this type of schedule for several data items for transactions with timestamps 1, 2, 3, 4, 5. So you can see that the timestamps of this T1 to T5 are 1, 2, 3, 4, 5. And now you see that T5 does a read X, and then T2 does a read Y, then T1 does a read Y. So as T5 does a read X, then this read timestamp of X will be set to 5, which is the timestamp of T5. When T2 does a read Y, then the read timestamp of Y will be set to 2. And then when T1 does a read Y, then of course it is reading, but the timestamp of of Y will still remain as that of T2. That means it will still remain at 2. So and now T3 is trying to write Q. Okay, so so when T3 is writing Q, so we see that so it is okay because T1 and T2 read Q and their timestamps are before that of T3, so it is okay to write Y by T3 and write Z by T3. Now you see that T5 is reading Z and that was produced by T3, so it is allowed to read that value of Z. And now the problem is that this when T2 is trying to read Z, So it was supposed to read the value of Z that was there before T3 did the write. So hence it is aborted. And likewise, you see that the write W of T3 also will be aborted and so on. So recoverability and cascade freedom. Problem with timestamp ordering protocol. Suppose Ti aborts, but Tj has read a data item written by Ti, then Tj must also abort. If Tj had been allowed to commit earlier, the schedule will not be recoverable. Further, any transaction that has read a data item written by Tj also must abort. This can lead to a cascading rollback, that is a chain of rollbacks, which we have discussed before. So often transaction is structured such that its writes are all performed at the end of its processing. All writes of a transaction form an atomic action. No transaction may execute while a transaction is being written. A transaction that aborts is restarted with a new timestamp. Solution 2 is that some limited form of locking, means a mix of considered to take care of the cascade, this cascading rollback and recoverability issues. The other point, so this was a classical timestamp based protocol, read and write. Now there is a bit of improvement on top of it, which is called Thomas's write rule. Now this Thomas's write rule, what it does is there is no change in the first part about read. Even for the write, there is no change other than for the second. Okay, so for the second, there is a simple change that is suggested in Thomas's write rule. So what happens is that if we see, let me first go to that rule. So in which these obsolete write operations may be ignored under certain circumstances. So when Ti attempts to write data item Q, if timestamp of Ti is less than write timestamp of Q, then Ti is attempting to write an obsolete value of Q, which is what we had mentioned before. Okay, that is at point number 2, that Ti is attempting to write an obsolete value of Q. And normally that write was rejected and Ti was rolled back. But what this rule says is that rather than rolling back Ti as the timestamp ordering protocol would have done, this write operation is simply ignored. Okay, so otherwise this protocol is same as timestamp ordering. Now, why it is ignored is that if you see that in this situation, that see Ti is attempting to write an obsolete value of Q, and Tj has already or some transaction Tj has already written the value of Q and accordingly updated the write timestamp of Q. So Ti is trying to write an obsolete value of Q. Now, why at all roll back Ti? Because then many transactions might get rolled back. To simply ignore this write. Why we can simply ignore this write? Because even if this write is ignored, then what would have happened? The transaction say Tj that wrote to Q and accordingly updated its write timestamp, its timestamp will remain as the write timestamp. So even if Ti is trying to write an obsolete value of Q, if we simply ignore it, then also the database will have the value of Q that is written by, say, some Tj that updated that write timestamp of Q, and that is what we can let it remain, because that will not make any difference. So this allows greater potential concurrency, because some of the transactions are not rolled back, so which means that we have higher concurrency, and it allows some view serializable schedules that are not conflict serializable. So this is an example of a protocol that can result in the generation of view serializable schedules which are not conflict serialized. So there is another approach which is called validation based protocol. So we had locking based protocols, then timestamp based protocols, and now validation based protocol. Now what it does is that execution of transaction Ti is done in 3 phases. First is the read and execution phase. So transaction Ti writes only to temporary local variables. The validation phase, transaction Ti performs a validation test to determine if local variables can be written without violating serializability. And if the validation is passed, the updates are applied to the database. Otherwise, Ti is rolled. So what are the detailed steps? The 3 phases of concurrently executing transactions can be interlinked. So some transaction can have its read and execution phase while the other is having a validation phase, while another could have its write phase, and another again can have validation phase, and so on. So, but each transaction must go through the three phases in that order. That first, the read and execution phase will occur for a given transaction, then its validation phase, then its write phase. So, assume for simplicity that the validation and write phase occur together, atomically and serially. That is, only one transaction executes validation write at a time. So this is also called optimistic concurrency control, since transaction keeps on executing fully in the hope that all will go well during validation. So what it does is that, see, the point, the basic underlying reasoning is that most of the transactions which are occurring concurrently, as long as they are actually updating different data items, so there is no issue of loss of serializability. As we know that this serializability is talking about this conflicting instructions of read queue and write queue on the same data item queue. So if they are working on different data items Q1 and Q2, so there is not going to be any form of issue with concurrency. Now, if you consider a database which has hundreds or thousands of tables, and if you consider these tables at the data items, then what will happen? It will mean that some transaction will be working with T1, another maybe with T2, and what I mean is some transactions means some concurrent transactions, the transactions that are getting executed at the same point of time. So unless all of them are actually updating or reading from the same table T1, so there will never be any issue in concurrency or with the isolation property. So, but if you consider timestamp based protocol and also the locking based protocol, even if eventually these are all affecting different data items, still what will happen is that they will have this overhead of using logs, which means some resources, or using timestamp based protocol. So what we see is that for every data item, I have to maintain a read timestamp and a write timestamp, and those are to be updated, and all the checkings are to be done. But most of the time, maybe the transactions that are getting executed concurrently in a schedule, they are actually working on different data items. So that is why this validation-based protocol was proposed. So, and it's called optimistic concurrency control, that the individual transactions keep reading and read and execution phase. So they write only to their local copies of or temporary local variables of the data. They do a validation to check that there is no conflict. And if the validation is passed, then in the write phase, the data is actually written to the database. So each transaction has 3 timestamps. Now you see that it is different. So it has got 3 timestamps for each transaction. Okay. So which is different from having a timestamp for each data item. Because in each data item, so no matter whether the transactions are updating or not, you have to have all those timestamps. Here, each transaction has 3 timestamps, and as the transaction is completed, we do not need to worry about their these timestamps anymore. So one is start TI, one is validation TI, the other is finish TI. So serializability order is determined by timestamp given at the validation time. So what is start TI? The time when the transaction TI started its execution. Validation TI, the time when TI entered its validation phase, and finish TI, the time when TI finished its write phase. And serializability, as I said, order is determined by timestamp given at validation time. That means the serializability order is the order of the validation TIs for the various transactions. So this protocol is useful and gives greater degree of concurrency. Probability of conflicts is low because the serializability order is not pre-decided, and relatively few transactions will have to be rolled back. So the validation test is very simple. If for all TI with TS-TI less than TS-TJ, either one of the following condition holds. The finish TI is less than start TJ, that means that TI has finished before TJ started, or start of TJ is less than finish of TI, but it is less than validation of TJ, and the set of data items written by TI does not intersect with the set of data items read by TJ. So that means that although TI has not finished when TJ started, and it is also less than the validation of TJ, but what it means is that they do not intersect in any data item, so there is no conflict. So validation will succeed and TJ can be committed. Otherwise, validation fails and TJ is aborted. Justification: either the first condition is satisfied, as I said, and there is no overlap to execution, or the second is satisfied and the writes of TJ do not affect reads of TI since they occur after TI has finished its reads. The writes of TI do not affect the reads of TJ since TJ does not read any item written by TI. So because of this, the validation test is passed, and then this transaction, this TJ can be allowed to commit. So it guards against cascading rollback as actual writes take place after the transaction issuing a write has committed. So this is an example of a schedule produced by validation. So we see that read B B equal to B minus 50, read A equal to A plus 50, read A validate and then display A plus B, and then that is done by T25, and T26 what it does is that it does a validate, and then as we said that after it validates, then it will do the writing. So T26 does the write B and write A after the validation step. So those are about, most of these are about concurrency control, where we want to maintain very good consistency of the data, both in terms of read as well as write. And that is why we talked about these timestamp based protocols. Today we talked about timestamp based protocols and validation based protocols. In our last class, we talked about this locking based protocol. And here we are so overall, these were all three types of protocol that wanted that ensured rather that high degree of consistency is maintained. Now, sometimes if you want to ensure this high or strong degree of consistency, then the concurrency tends to suffer. So many, because you see that suppose there is a transaction that reads a lot of data items, okay, and then displays, say, the sum of balances of all accounts in a bank. So it will read so many different data items, all the accounts and their balances, and it will have to acquire a read lock, or it will have to update the read timestamps. And in between, no other transaction will be able to write to that. So that means that any other transaction which is even updating the balance of a single account, so that will not be allowed because another transaction is reading the sum of the balances of all the accounts. Or there are cases, for example, database where we want some statistics. For example, say number of say this COVID vaccine given at any point of time. Now we want to see the total. Now at that point of time also more such writes are happening when more such vaccines are being administered. So the database is also getting updated. Okay. Now, of course, that also means that if we try to get the total number administered so far, I have to stop updating of the currently administered numbers. But it is not required because we want only a statistics that roughly how many have been given, whether exactly say 3 million have been given or 3 million and 1,000, it does not really matter. Okay. So these are some cases where we can trade off accuracy for performance. Now, SQL 92 standard specifies several such levels of consistency, like weak levels of consistency and the usual one. So first of all, that the serializable level is the default level of consistency. So that is what we have so far discussed. The repeatable read. Now, repeatable read is only committed records to be read. Repeated reads of same record must return the same value. However, transaction may not be serializable. It may not find some records inserted by a transaction, but not find others. So what it means is like this. Suppose there is a transaction, and say it is reading, say, the account balances. Okay. Now, in the transaction, first it reads, say, all the accounts balances, and say there are 1,000 such accounts. So it read those 1,000 accounts and their balances. If this transaction reads the same balances of those 1,000 transactions once again, that is what is called repeat the read, it will again read the same values of those same accounts it will read, and it will also read the same values of their balances. So that is what is called repeatable read. What is not guaranteed in this is that if there is another transaction which adds a new account, say 1001 account number with a new balance, so first time the second one may be not be there, but second time the second one also will be there. So that account number 1001 with its balance, so that may appear in the second read but not in the first. So that means that same records, if they are read, so the balances cannot be updated. So of account number 1, if it was 100 at the time of first read, that cannot be changed if the read is repeated by the same transaction. But as it says that a transaction may not be serializable, it may find some records inserted by a transaction but not find others. So now, as I said, while this read is repeated by this transaction, say T1, if T2 has added another account 1001 with a new balance, so in the second read, this will show up, and in the first T1 is reading the entire table, so T2 will not be with a, say, a read or shared lock, then T2 will not be able to get an exclusive lock and then write, as I was saying. But so that would have made it a completely a serializable schedule. But suppose we allow new transactions to insert records while this read is happening. So in that case, it is called repeatable read. So the same records which are read again and again, you will get the same value, but it might get some new records inserted in the process. Read committed means, so as we are going from the first bullet point to the second and third, we are actually making weaker and weaker levels of consistency, which actually will also lead to higher and higher level of concurrency. Okay. So read committed means only committed records can be read, but successive reads of record may return different values. So that means that when this transaction, as I said, for repeatable read, T1 read the account balance of say account number 1, say it was 100. So then it reads account balance of say account number 2 and so on. So if it goes back and reads 1, in between another transaction also might be updating the value of the balance of the account number 1. That was not allowed in the repeatable read, but read committed will allow that. But how is it different from read uncommitted? So assuming that this transaction T1 first read the balance of account number 1, which was 100, then it comes back and reads again the balance of account number 1, and in between another transaction has made it as 150. Then in this second read, T1 will read the value as 150, but it is committed, means that by committed it means that the transaction T2 that changed the value of 100 to 150, that has committed. So if T1 now reads the value of the balance of account 1 as 150, that is a committed value. So that is not going to result in any incorrect read. The final one, that read uncommitted, means that even uncommitted records may be read. So that means that if T1 first read the value of account number 1 as a balance of 100, and then T2 changed it to 150, now T1 reads it again, it will read 150, but T2 did not commit. So T1 again reads it 150 and proceeds. But now if T2 rolls back, so T2 did not commit that value 150, but T1 in its second pass went ahead and read that value of 150 and proceeded. So that is the that is called the read uncommitted. So that means even uncommitted records may be read, and that is the weakest level of consistency. But as you can well understand, that this will also result in highest form of concurrency. So almost no additional overhead will be required for ensuring the isolation. Now, why it is allowed? Because some cases, as I said, that even if someone, say, when I am reading the total count of the number of vaccines, suppose some center has added 100 more vaccines but did not commit, and later on it reverted because it found that no, it was not 100, it should have been 200. But I read in the process what is the total number, so it is 3,100,000. So you see that I might be allowed, because even if it is if it gets rolled back, so I'll be off by maybe 100 out of 3 million, which may not really matter. Okay, but it will give a very high value of concurrency, because so many people might be reading how many such vaccines were administered today, that read is occurring again and again and again, and writing is occurring less frequently, and you do not want those committing of those rights before these reads are allowed to proceed. So what it means is that we really don't care even if some uncommitted reads take place, which might later be rolled back. So lower degrees of consistency is useful for gathering approximate information about the database, as I was saying, that some database systems do not ensure serializable schedules by default. Although the first one we said serializable is the default. So there are what we say exactly as serializable, like conflict serializable schedule and so on. So some databases say that they are ensuring serializable schedules by default, but they do not actually implement like the timestamp based protocols or validation based protocols or locking based protocols. They use a different concept which is called snapshot isolation. So that is their default, which they term as serializable schedules, but there is some theoretically some difference between the schedules that get generated by snapshot isolation and the ones which are generated strictly by conflict serializable schedule generation protocols. So that is what we need to just keep in mind. Actually, these snapshot isolation, etc., these topics are taught more in the course on advanced database systems, which is offered in the autumn semester. So that brings us to the end of this chapter, chapter 15. And for this chapter, you have to focus on these particular sections and subsections. So if there is any question, you may please ask. Otherwise, I will proceed with the next chapter, which is chapter 16. So is there any question? Okay, so if there is no question, so let me start the next chapter, which is chapter 16, and I believe you can also still see my screen, it is shared, and our recording is also on. So let us understand the basic concepts of recovery system. So far it is so good. We talked about these properties of isolation. We talked about the property of atomicity, but we need to address the property of durability. Okay. Now, what is durability? That suppose you are carrying on a transaction, and this transaction has 5 different instructions. After first 2 instructions, the system crashed. Now, this term you have to keep in mind that when we say system crash, I mean, say the power goes down or there is a memory error and so on, so that you have to reboot the system. But this system crash, this term in this context will not include the situation when there is a disk crash. Okay, so disk crash is treated differently from what we mean by system crash. System crash could be due to some hardware issues, like as I said, just the power goes down, or there is a memory error, or there is a divide by zero kind of logical software error which will cause it to get stuck. So those are what we call as system crashes. And this transaction failure, as I said just now, this could be logical errors due to some internal error condition or system errors. And this is what we call system crash. So it is the fail stop assumption, as I said, non-volatile storage contents are assumed to not be corrupted by a system crash. So that means the database systems have numerous integrity checks to prevent corruption of disk data. So the disk data can have different types of RAID configurations and so on, and integrity checks like CRC checks and all that. So what we are saying is that system crash will will be such that the disk actually survives a system crash, and there is a disk failure. So there is a head crash or similar disk failure that can destroy all or part of our disk storage. So it is assumed to be detectable. Disk drives use checksums to detect failure, so it can be detected. So we'll consider different types of situations. So consider a transaction TI that transfers $50 from account A to B. So we have, as we have studied, there are two updates. You subtract 50 from A and add 50 to B. Then TI requires updates to A and B to be output to the database. A failure may occur after one of these modifications have been made, but before both of them are made. So modifying the database without ensuring that the transaction will commit may leave the database in an inconsistent state. So not modifying the database may result in lost updates if failure occurs just after the transaction commits. So recovery mechanisms have two parts. There are certain actions that we need to take during normal transaction processing. So whenever we are updating things in the database, we have to do a little bit of extra work, so that if that is a point number two, that if there is a failure, we will be able to take certain actions to recover the database contents to a state that ensures atomicity, consistency, and durability. So just understand that what we are talking about is going to happen even if there is no concurrent execution of transactions. Even if there is a serial execution of transaction, still these problems are something that we have to keep in mind. Because if there is just one transaction which is transferring 50 from A to B, then we have to ensure that indeed either nothing happens. So account A has its initial balance of, if 50 is taken from A, it becomes 1000 minus 50, that is 950, and B becomes 2050, then actually everything is good. But if only 50 is reduced from A but not added to B, that is something we cannot allow, even if, say, there is a system failure of some form. So that is what we are actually talking about here. So remember that this last bullet, the recovery mechanisms have indeed two parts. One is the actions we need to take during normal transaction processing, which will ensure that enough information exists to be able to recover from failures. And the second part, that because we have taken action during the normal execution, when there is a failure, then we will be able to take a well-defined set of actions to ensure that the properties of atomicity, consistency, and durability is maintained. Now we have to look back a little bit about storage structure, which has already been discussed by Professor Ghosh. So there is volatile storage like main memory, etc. There is non-volatile storage which survives system crashes, but they may still fail losing data. And then finally, we have this concept of stable storage. So I mean, call it quote unquote mythical form of storage that survives all failures. And it is approximated by maintaining multiple copies on distinct non-volatile media. So you can see the book for more details. So for us, the stable storage means that if we say that something is written to the stable storage, it simply means that that data that is written to the stable storage will survive not only a system crash, but also a crash of the disk. So for us, stable storage means a form of storage which will survive disk crash also. So it could be because you are writing to multiple copies or something which is not going to, or you are writing in a different system, so that even if this system crashes, its disk crashes where your main transaction is going on, the storage, which we term as a stable storage in that second server, is not going to fail. So there are many different ways of stable storage implementation. So as I said that you see the book for more details, so you can maintain, as I just now mentioned, multiple copies, etc. Okay, so you can make it physically in a different location. At least that you should not have that in the same server box or even in the same rack if you have a rack of servers, because if for some reason there is a major power swing, all the disks in all the servers in a particular rack of servers might crash. So it is good to keep it in a different rack of servers, or you can keep it in a physically a different location and so on. Of course, more you try to spread out while storing data in the stable storage, also it will incur more network latency. So those are also to be taken care of. So that's why we said that you can take a look at the book for some more details. So as I said, 2 copies, etc., and there are many different forms. As it's very well known that hardware RAID systems, okay, which provide some form of implementation of this concept of stable storage. Now we come to something very important. So data access. So look at it like this: the disk has got the physical blocks, which we have studied also in the context of storage and all. So there are physical disk blocks. There are what are called buffer blocks. The buffer blocks are the blocks that are residing temporarily in main memory, and block movement is between disk and main memory. These are initiated through the following 2 operations. Input B means transfer the physical block B from the disk to main memory. So it goes to the main memory's buffer block. And output B means transfer the buffer block B to the disk and replaces the appropriate physical block there. We'll have some figures to explain this. We assume for simplicity that each data item fits in and is stored inside a single block. So this is the figure I was referring to. So you look at this very carefully. So we have the disk here. We have this physical A and B. In main memory. So see, it is disk here, it is memory here. So in the buffer, there is a buffer block A that corresponds to a physical block A. There is a buffer block B that corresponds to a physical block B. And then, as we said, that input and then the physical block as parameter. If we do an input A, then this physical block A is brought from disk to the buffer block here in main memory. Similarly, this is buffer block B. If we execute an output B, so this buffer block B, it will be written to the disk block B. On the other side, let us assume that in this buffer block A, there are many data items, because buffer block could be of, say, 4 kilobyte size or something, okay, depending on the size of the disk blocks. It will contain multiple data items. One of the data items is, say, X, which is in buffer block A, and there is in buffer block B a data item called Y. Now, consider this transaction T1 and a transaction T2. So this is the work area of T1, this is the work area of T2. And then the values of X and Y in the local areas of T1 and T2, we denote as X1, Y1 for T1 and X2 for T2. Okay, so that is the notation that we have here. So if you look at this, that say if T1 is reading X, okay, as you see, read X. So what happens is this read X, it will issue, and if this X is in buffer block A, let us consider if X is in block A, and if this block A is already in buffer block, this value of X will be available here in T1. If not, then if this X is in some buffer block, a disk block in the disk, and that block is not there in the buffer block, then an input of that disk block will have to be done, and then only T1 will be able to read it, because this T1 cannot directly read it from the disk. So data will come from the disk to the buffer block, and from there to the work area of T1. Now you see that if T1 also wants to change the value of Y, and it wants to write a value Y1, then it must have read that value of Y here to a read Y, and then it changes the value to Y1, and then it issues this write Y to write the value, new value of Y, which is Y1 in the buffer block B. Likewise, work area of T2, so if it reads the value of X, suppose it gets the value of X as X2, or we denote the copy of this X in T2 as X2, copy of X in T1 as X1, copy of Y in T1 as Y1, and so on. So you see that each of them work in their own area. Now, something that we need to understand is that when a transaction writes the value of Y1, remember, and this is very important, that Y1 gets written to the corresponding buffer block, in this case buffer block Y, which has buffer block B, which has Y. Now, once it is written to the buffer block and we get a commit of the transaction, we are good. Means that from the transaction point of view, the data has been committed. But indeed, this is very important. It means, or it could mean, the data only went and got written in the buffer block. It has not been flushed yet to the disk block with an output B command or instruction or whatever it is, operation. So from the transaction point of view, it reads from the buffer block, makes some changes, writes to the buffer block. If it is written there, it commits. From T1's perspective or T2's perspective and so on, the data indeed has been committed, and the user gets a message that your data has successfully been saved. But actually, the database management system might not have flushed this buffer block B yet to the disk block B. But because to T1's point of view, this Y has been written into successfully in the buffer block and it has given a message that it has been committed, then we should ensure the property of durability, that even after this, if the system crashes, means this memory crashes or there is a power shutdown, then as you can understand, this buffer block will be gone. But we have to ensure that still when the machine restarts, this job that changed the value of y to y1 by transaction T1, that should not have to be repeated. Okay, so the recovery mechanism should be able to automatically ensure that whatever value was written by T1 in the buffer block possibly, and maybe it was not flushed to the disk block before the system crash, then also this T1 should not have to be redone. Okay, so by the user. Okay, so we'll see what it means to do redo and etc. Now the other part is that suppose that T1, suppose it changed the value of X and it was supposed to change the value of Y, like this account A and account B transferring $50. So in that case, it only changed X and did not change Y, and now the system crashes. Then also it should be ensured that for the atomicity property to be enforced, then what we call the transaction should be rolled back. So the value of X also should be written back to the original one. Again, very important is that suppose, as I said, the transactions are only interacting with the buffer blocks and the database management system otherwise is deciding when to flush the buffer blocks to the disk blocks. So if T1 changes the value of X here in the buffer block A and it did not yet change the value of Y in buffer block B, and the database management system felt that, oh, I have to bring in new blocks, there is not enough space, I will flush buffer block A. If it flushes buffer block A, then what will happen that T1 only changed the value of X1 in the buffer block A. It did not yet change the value of Y in buffer block B, but X has been flushed to the disk along with buffer block A. And now suppose there is a system crash. Then what will happen? The disk will apparently show the value of A to be the one that was written by T1. But then, of course, T1 could not complete or commit. And now part of the transaction got executed, which is even got written to the disk, but the other part is not done. But even in such cases, we have to ensure that the recovery mechanism actually is able to recover the database from this situation where that effect of T1 in changing X should be rolled back. Okay, and it should be set back to the original value. Okay, so the entire protocol should be independent of when the system is flushing the buffer blocks to the disk block. But of course, we'll study that we have to bring in certain restrictions so that it is not done just like that. So there is something else to it. So this is what I have already mentioned. Okay, that what is readx, writex about local values. So this is what I have been repeating a few times for your understanding, that output bx need not immediately follow writex. So that is what I said. This writex is done, okay, or write y is done, that output need not follow immediately. Okay, so transactions perform readx before accessing x for the first time. Writex can be executed at any time before the transaction commits. To ensure atomicity despite failures, we first output information describing the modifications to stable storage. So this is what the point is. So it is despite failures, atomicity is to be guaranteed. So we first output information describing the modifications to stable storage without modifying the database itself. After that, we'll make the modification, and for that we study what is called log-based recovery mechanism in detail. So this is the introduction to recovery, and we'll study this recovery mechanism that makes use of log. Again, do not get confused with log with lock. Okay, lock was in the context of concurrency control, and log-based recovery is in the context of recovery. Okay, we'll stop here, and we will start discussions on log-based recovery and complete that discussion tomorrow. So that is about a few, like about 20 or so pages. Okay, so which we'll take up in our tomorrow's class. So we'll stop here. So if there is any question, you may please ask. Otherwise, we'll close the class here. So if there is no question, I am stopping the recording.